It's great to see everyone come back, and we'll keep the momentum going here. Again, I want to put out our thanks to OCP for sponsoring this initiative, this session. Very much appreciated. It's my pleasure just now to introduce the chair of the session. Dr. Amarjeet Basra is going to be our chair. He's currently chief scientist at OCP North America, and he drives transformative innovations that translate cutting-edge fertilizer research into practical solutions for sustainable, climate-smart agriculture. And his career spans academia and industry, multiple continents, including senior research roles at leading institutions like the Punjab Agricultural University, University of California, Davis, go Aggies, I'm a grad of there, Wageningen University, the University of Western Sydney, Hawkesbury, and major agricultural companies such as Monsanto and Syngenta. Dr. Basra, please take over.
Come on, front, the chairs up here.
Thank you, Jim, for the introduction. Thank you. Good afternoon, everyone, and welcome to our session on new developments and initiatives related to phosphorus sustainability. As Jim said, I am Amarjeet Basra with OCP North America. I'm with OCP North America, which is a subsidiary of OCP Group, headquartered in Morocco. We are one of the largest phosphate fertilizer companies globally. And it's my pleasure to serve as your session chairs today. And we are grateful to the organizers for this opportunity and also all of you for coming and joining the session. So every day we face a critical challenge, how to feed the growing population sustainably. And one of the critical, the heart of this challenge is a finite resource, phosphate. It cannot be synthesized, limited reserves, has to be used and reused sustainably. So at OCP, we are the active stewards of this vital resource for humanity. Being one of the largest reserves in Morocco, where the phosphate reserves are located. So we are stewards of this vital resource, and we have a clear mission to bring phosphorus to life sustainably, from mine to farm to recycling. So the whole entire value chain, we work to build this sustainability around phosphorus value chain. Our approach is farmer-centric, helping farmers to grow and building resilient and sustainable agriculture. We invest in innovations that enhance efficiency, improving how phosphorus is used and reused. And as I said, sustainability drives our entire value chain, from our re-engineering our operations to supporting farmers with the right amount of customized phosphate fertilizers. So that's our differentiation, that we customize the fertilizers to the crop, to the soil type, and like that, and the right amount using the 4 R's principles, so that we contribute to healthier soils and cleaner waters. Some figures. Our company is over 100 years old, so we have a century of experience in large phosphate reserves in Morocco that make us a cornerstone for global food security. If in terms of figures, OCP today produces 1/3 of the world's phosphate, 1/3 of the world's phosphate, and operates across 6 continents. So by 2026, our crop nutrition solutions will serve over 50 million hectares worldwide, advancing both food security and environmental health. So today's session is around new developments and initiatives, and that's one of my roles as a chief scientist, looking at those new developments, initiatives, innovations. And we have an excellent group of speakers who will share new insights and initiatives that advance phosphate sustainability. Let's get started. To kick off the session, I'm delighted to introduce my colleague, Brian Bowman. So Brian is the Agronomic Science and Innovation Manager at OCP North America, where he leads the technical development of innovative crop nutrition solutions. He earned a PhD in water resource science from University of Minnesota and has expertise in soil fertility, crop nutrition, and digital agriculture solutions. Welcome, Brian. Thank you. Yeah.
All right. Okay, so the title of my talk and the focus of it is really on phosphates as fertilizers, a bit on agronomic applications, but I want to spend some time to contrast a bit on the outcomes of agricultural use of phosphate. Let's look upstream and spend some time thinking about phosphate production and where does phosphate come from. So just to give you an overview or an outline of what we'll be going through today, we'll be talking about the production of phosphate fertilizers, a review of key fertilizers, some innovations, old and new, and then some agronomic considerations to end. So I won't spend too much time on this. Amarjeet did a very good job of describing OCP Group and our mission. But what I think is important is the place that OCP plays and the place that, from a global perspective, where we sit when we think about the global phosphate resources and reserves. There has been an increase in rock production, rock mining, to support the demand from various uses, agriculture and other industrial applications. And that demand is projected to increase, right? That's what the central figure is looking at when we look at this report from IFA, or supported by IFA, and we look into the future and we say, okay, demand continues to increase as population and other uses increase. And we can look out to the future and somewhere, given current uses and reserves, we have about 220 to 450 years of economic reserves available, right? And new technologies and new efficiencies will help us bridge that gap and continue into the future as we deal with this, managing this finite reserve and resource. When we look across the globe, there is phosphate in many places, both sedimentary and igneous forms of the mineral. The sedimentary forms, those are the ones that are formed by historical marine sediments. That's the vast majority of the reserves. Lower production cost and a higher raw grade. The igneous phosphates are important reserves in some places that are typically not extracted or used. And just the key difference. When putting OCP into the context, right, as Amarjeet was describing in his introduction, OCP has a significant component of the world's phosphate reserves. We're the stewards of those reserves, and we take that responsibility seriously. Have a variety of mine sites and production sites across Morocco. And for those of you that might not be familiar, Morocco is located in the northwestern part of Africa, right by the Mediterranean and Spain, which is a key jumping off point to transportation of the resource of phosphate products around the world as well, which is why we're able to serve so many markets efficiently. When you're in these mines, you see that they're formed in many different layers, right? Different constituent impurities or ore grades of the rocks. And the extraction process really is done in this sequential manner as you work through the different layers, removing the sedimentary components, right? The rock layers that don't have the usable phosphate. And even thinking about differences within the phosphate ores themselves, impurities or beneficial components. That rock is not rock is not rock. And as this rock is processed, it moves through a variety of screening and washing and cleaning and separation to go through this beneficiation process, where we're taking the lower grade ores or the ore as it's extracted and refining it into a rock that's ready for a manufacturing process, right? A chemical manufacturing process, either to react that rock with some acid. Phosphate rock itself, as we'll talk about, is not necessarily plant available, right? We'll talk a little bit about what does plant available phosphate mean in the context here, but this is the beginning, the mining, and then is the beginning of the process, the extraction, and then it goes through a variety of potential different chemical processes. And we're going to be looking at this flowchart or versions of it. Some of you may have seen this or similar figures before. When you take the rock and you add different acids or remove certain constituent components or re-react it through this chain process, we have the phosphate fertilizers or phosphate products that we know and love and that have been, part of the use in agricultural applications for over the last 100 years. And we'll talk about each of these in particular. When you look backwards, and I apologize that the figures on the right are small, I'll just narrate them if you're not able to see directly. Both on a global and a US perspective, the historical in say the 70s and 80s, right, as we fix that as our starting off point, the superphosphates, single superphosphate and triple superphosphate, were the original high analysis P fertilizers, or some of them, and they had the predominant share. As technology developed and economics of production changed, we saw a much greater rise of the ammoniated phosphates, MAP and DAP, and that's the paradigm that we're still currently in. We see that the global P fertilizer use really remains dominated by the ammoniated phosphates, although the superphosphates still do have a role in certain markets. So let's talk a bit about some of the key fertilizers. The first being rock. You can directly apply phosphate rock. It's something that the phosphates can be more available in acidic soils, highly acidic conditions, just because the rock needs to be acidified to be solubilized. And when you look at those reaction processes of producing MAP or DAP or a single superphosphate or triple superphosphate, it's an acidification process. Adding acid to the rock solubilizes the minerals, right? The apatite minerals. Typically rock, and it's going to vary based on the grade itself. It might be somewhere between 28 and 35%, with about 3% of that P2O5 being citrate soluble. The superphosphates, as I mentioned, the key difference between them is the acid that's used to produce them. Either sulfuric acid to produce single superphosphate or phosphoric acid to produce triple superphosphate. When you go back into the history of phosphates and earlier 20th century chemistry or 19th century chemistry, sometimes these names seem a little strange to us now. And so we deal with, triple superphosphate as maybe twice as good, in terms of its P2O5 analysis. But what you see when you look backwards is the impurities or the grades of the fertilizers changed over time. Now that we have commodities markets and these fertilizers have understood definitions, those can change too, right? And so the history of phosphate production really was continuing to produce higher and higher analysis products. When you have the ammoniated phosphates, these have a high total analysis grade of nitrogen and P2O5. There are some differences in regional preferences, right? DAP, diammonium phosphate, is more basic, has a higher pH, whereas MAP, monoammonium phosphate, has a lower pH. I should mention too about the superphosphates, because they have potentially unreacted or do have unreacted acid in them, the pH of those granules is more acidic. In some areas, especially as sulfur has become more limiting in terms of agronomic considerations, the sulfur enhanced phosphates, the NPS products, have become more common, especially in crops where sulfur is required or is essential for production of those crops. There's a variety of different sulfur technologies or ways to incorporate sulfur into the granule. And typically you see this as either as a sulfate sulfur or an elemental sulfur. Those have different profiles in terms of their plant availability and also the impact that they have on the total analysis, right? Because elemental sulfur is just sulfur, whereas the sulfate sulfur has the oxygen too, right? And that's important to keep in mind with these fertilizers is the grade can be affected by what else is included that's not just the plant nutrients of interest. Polyphosphates, liquid fluid fertilizers. Essentially, in this case, you're taking a phosphoric acid, adding in ammonia, and moving off water. This is a common constituent component or part of the same process that's used to manufacture starter fertilizers, right? Liquid starter fertilizers. This can be a key phosphate source for crops in cool areas or that are going to be responsive to a starter fertilizer. And it's a combination both of orthophosphate as well as polyphosphates. So just the removing the water produces this stable fluid fertilizer. Just a quick comparison, right? We see that there's a variety of different phosphates we have available, and let's talk about some more, right? We're not done here. This isn't the full list. So I put phosphate innovation a little bit tongue in cheek because one of the things that we've spent some time doing, and I would encourage those others to spend some time doing too, is looking backwards. There was a significant amount of fertilizer innovation that happened here in the United States, as well as other places in the world, right as investments were being made into improving the fertilizers, the inputs that are going to sustain productivity, right? Coming out of the Depression era, the TVA, National Fertilizer Development Center, did a lot of the core research in manufacturing and agronomics that produced the phosphates we have now. As much when we look at phosphates, think of the history of this story, and let's think about maybe some of the phosphates that we lost along the way, right? How did we get to where we are now, and what did we leave behind that maybe we should consider again? And how can we think about phosphate fertilizer innovation, technology development, when we move from this paradigm of public supported innovation into one that's more private supported or private funded innovation? And are there lessons or collaborations that we can lean into to take advantage of the resources that the historical legacy resources and learnings that were previously invested in? So I added in a few new fertilizers to our chart. This is not a comprehensive list. I picked 4, somewhat arbitrarily, but you could continue to add into this matrix, right? Different reaction processes. We'll talk about fused tricalcium phosphate, enriched superphosphate, ammoniated superphosphates, as well as struvite. So fused tricalcium phosphate. One of the things to keep in mind with the early phosphorus production technologies was they derived from or came out of the infrastructure that the U.S. government had implemented as part of Depression era works projects like the TVA, as well as munitions production for World War I. And so some of this production for fused tricalcium phosphate, they had the crazy idea that if we put rock into an oven that's connected to this big hydropower dam, we heat it to 1400 degrees C, we can break down the crystalline structure of this rock. And this became a fertilizer that was widely used in the Tennessee Valley in the 30s, which is crazy, right? I mean, it's just crazy to think about that amount of energy that was used, or the intensity of that production, or how this is a fertilizer that was core to the adoption of improved phosphates, and it's not talked about, right? Because it's not commonly used. We've made better phosphates, but an important technology that was developed along the way. The ammoniated superphosphates were really this bridging technology between single superphosphate and triple superphosphate and MAP and DAP that we have today, right? We don't just jump from one paradigm to another. We moved along this gradient as we switched from the superphosphates to the ammoniated phosphates, and just thinking, well, how could we change the superphosphates by adding in ammonia? And some of the technologies that were used to really improve granulation, you see this mixing or fusing, right? We didn't end up with the ammoniated superphosphates as an end state because in a lot of ways, MAP and DAP did the job better. But it's an interesting technology to think about, especially because the addition of ammonia changes the phosphate mineral. So you can manipulate or modify the chemical compatibility of the fertilizer, the solubility of the fertilizer, and achieve really different customized or tuned grades, right? That we don't necessarily need to end up with these endpoints, that this is a technology and approach that could really modify fertilizer or tailor it to meet a local needs or local environments in terms of phosphate solubility, nutrient analysis, and the like. In a similar way, the enriched superphosphates are really just a blend between SSP and TSP, right? Why not have some ratio of sulfuric acid to phosphoric acid, right? You can tailor or customize or think about how much sulfur do I need as part of a superphosphate, and you can bridge between this combination or this balance of P to S, right? We just talked about a balance between N and P. Here's a balance between P and S. And you're going to have, again, different minerals with different properties that might be better suited for some environments or some soils versus another. Finally, I want to talk about another phosphate. This one, you can be, we heard some discussion in the previous session in some of the AI, just saying this is, as an example, either something that can be reclaimed from wastewater or produced via some of our existing components, right? The addition of the magnesium oxide or some other magnesium component, we can manipulate and modify these phosphate minerals to produce the fertilizer that we want. And so we're not necessarily, I think struvite is a great example, as some of these other are, in terms of saying we're not bound to the fertilizers as they are, and whether we're coming from a rock stream or some other reclaimed stream, there's ways to leverage the P2O5 that we have available. Some agronomic considerations. When we think about phosphate sources, one of the first questions that's asked after what's the guaranteed analysis, or what's the soluble or available P2O5, or what other nutrients does it contain, is, well, how well does it perform? When you bring a new fertilizer to the market, or even try and bring an old fertilizer like TSP back to the market, there's a seeing is believing mentality or mindset. And so agronomic testing or comparison for growers, for agronomists, for folks that work in extension is important, right? We can see on paper that yes, P2O5, they were providing the same amount of plant available nutrients, but that doesn't always mean that it's going to be available or provide the nutrition that plant needs at the time it needs it. And we see, especially in certain challenging environments, we'll talk about some of the considerations for challenging environments in upcoming slides, but in some places that are more forgiving in the soil, phosphate might be just as good as any other. In some cases, we know that's not the same. So as we think about these new sources of fertilizer, it's important to think about the agronomics and the comparison, right? And so the data I'm showing here is just some data that we've done from third-party trials comparing TSP to MAP and DAP. And what we see from this set of trials, the data I'm showing is, and this is from the core part of the Corn Belt, Illinois, Indiana, South Dakota, and that general area. We have agronomic equivalents, right? That we're providing the same amount of plant available nutrients, that you're not seeing a difference. You're not seeing a source effect, right? And that's one of the things that we want to consider as we're comparing and bringing new fertilizers to market is there an agronomic source effect that we need to be mindful of? What are some of the things that can drive the source effect? Well, one of the key ones is soil pH. The fertilizers themselves have some acidity or alkalinity, but their solubility in the soil environment is going to depend based on the pH of the soil, as well as the potential to form any secondary minerals or precipitates, or how the phosphate is going to react in the soil. And so in this figure that we're showing here on the bottom left, it's comparing the dissolution or the diffusion of superphosphates versus ammoniated phosphates, in comparing the top row, or the yellow bar, is a calcareous soil, so higher levels of calcium, whereas you have more of an acidic soil in the blue bar or the bottom line. Well, TSP and SSP they're calcium phosphates, right? So there are some challenges both to the dissolution and diffusion when you have this common ion effect, right, from the calcium. So we have to be mindful of what else is in the soil and how is that fertilizer going to interact in the soil. The same with seed safety. In areas where phosphate is placed with the seed, along to increase efficiency or availability, sometimes the level of nutrients supplied, especially in conditions where it's drier, you're going to have higher salt stress. That can vary across fertilizers too. And some of the functions of that variability are what salts are present, how soluble are those salts, what's the total load. It's not as simple as saying here is the salt index of a fertilizer and I will or I will not see an agronomic difference. Some of these things need to be demonstrated from either greenhouse or field trials too. Another key consideration is nitrogen losses, right? What else is in the fertilizer that we might not be applying on the basis of, especially for fall applications of phosphate in humid environments? The application of an ammoniated phosphate like MAP or DAP could lead to nitrogen losses between the time that that fertilizer is applied in the fall and when it's taken up in the spring. There is some research done at University of Illinois and University of Minnesota looking at the availability or the nitrogen that remained after a fall application. And what that study showed is that only about 1/3 of the ammonium that was applied in the fall was available to the plants in the spring. So it's important to keep in mind that depending on the timing of your application, there might be a better or a more appropriate phosphate to solve that job. And finally, we have to be mindful of how these fertilizers may react with other fertilizers. To give one example, superphosphates like SSP and TSP, they're not compatible in blends with urea. And so as we think about the way that fertilizer is stored on farm or brought from a fertilizer shed out to a field to be applied, understanding the fertilizer and its properties, the physical properties, handling with equipment, storage considerations, it's a really important thing too, because many of the pain points that we hear from our customers have to do with how, not of the fertilizer failing to perform itself, but as the fertilizer is being handled and brought to the field, are there ways to make that process better? And it's an important thing to keep in mind as we think about new phosphates, right? Can we solve some of these challenges of the existing phosphates and modify them or improve them to overcome some of these barriers that customers may have? So I'm really not sure how I'm doing on time, but if there are any questions, I'm happy to take them now. Thank you.
There are 5 pillars that have been selected under this strategic direction. The first one is really, again, as I said, the production, the scientific production is going to be at the core. What we produce, what the quality of what we produce, and how do we consolidate it to make it available to the end users. The second pillar, innovation and solution. Here, we're going to put a really a big emphasis on how whatever information or whatever interesting finding comes from the research, how do we team up with the partners to implement some of the innovations? How do we team up to implement some of the research findings? Again, for example, we don't deal directly with farmers, but we will have to team up with some institutions if there are interesting results to look into. The fellowship agenda is something that we will emphasize very much, in the sense that we think that phosphorus being a very, very important resource, it's important to grow new talent. It's important to grow new talent who will be interested in doing some very, very interesting work in this area. So this is something that is going to be very important. Policy engagement and advocacy also will be important. We will be promoting context-specific solutions through dialogue, briefs, fact sheets, and even events at the COP, for example. Knowledge packaging and outreach. We are revamping our website to make it more attractive, and then be able to communicate better through this lens also. The fifth pillar, institution development and strategic partnership, will be very, very key. Later on, I will talk about a platform that we have launched in Dakar, which is going to bring all African researchers together to look into the aspect of phosphorus and as a main nutrient, and see how action can be coordinated internally. These are some of the current flagships that we have been working on in 2025. As I said, we are revamping our website, but the Knowledge Hub, we are going to really beef it up to make sure that we put together all the production that we have to make it accessible and available to the end users, I mean, all the stakeholders. We are also going to partner with Purdue University to look at the flow of phosphorus along the food value chain, the entire food value chain. That will be done to quantify really the flow. But the good thing here is that they will be able to do this work for more than 100 countries. That's going to be available. I talked about the African platform that we just launched, the fellowship program, that is going to be very important for the years to come, but we are having a pilot this year as well. There is a series of fact sheets that are being produced. All of those are, I think, actually on the website already, covering 12 priorities. We are also reviewing the governance and operational framework of the institute right now. Now, this is the platform that we've launched. We still think through it, but at least it has been launched. We need to discuss with the stakeholders the governance structure, what will be the focus, etc. What are the modalities? All those things will be discussed later. Now, these are some of the 4 areas that I've selected that I think we can collaborate on. We can share data, we can design pilot projects, we can come together to organize joint policy dialogue, and we can partner also on fellowship. So these are some of the things that we think that if we work with you, it can be a win-win situation for all of us. So we are open for discussions on those areas of collaboration. So I'm going to leave 20 minutes, I think, to Gerard, because he has some very, very interesting stuff to share with all of us. Thank you.
Much more. You're totally in time. I'm impressed. On the second, let's have a look if I can do the same. So actually, we heard a lot about key issues related to phosphorus, that it cannot be substituted, that it's essential. And what's also very often around is that kind of fear, of running out of phosphorus. And this is very much also related to some fallacies that are out there. And what I want to do and show you here, oh, good, is actually related to that. And that means very often the dynamics in the system might not be considered. And when I build now a bridge to the AI contribution that we heard before, the question is also how to deal actually with sometimes wrong assumptions, how to deal, for example, with kind of fears in respect to kind of a peak or, as I said, running out of phosphorus. So what I present here is related also very much to a paper that's summing up what the Lab for Sustainable Mineral Resource did. And we are happy to share actually this material here. So you have my coordinates, and if you don't get access to the paper yourself, RCR paper, please just mail me. And who is we? This work was done by the lab. The lab itself is an interinstitutional organization or institutional framing. And actually, here I have to thank GPI for making this possible, namely for us working together between Freiberg, between Austria, between Oxford, between our colleagues in Boston. So this is the basis. And also with respect to the names you see here, Scholz, Boelmer, Mew, myself. So what did we do, and what actually is kind of the basis of this work? As I said, what about the dynamics? And the dynamics is not only at the demand side, it's also at the supply side. And let's make some thoughts about that. So what we see here, you see these historic trends, with respect to how much phosphorus actually was consumed. And there's not a big surprise. We see some kind of extraordinary events. We see here, for example, the event of World War. We see here issues such as related to crisis. We have COVID crisis, all that. And we see also changes in production capacities and strategies. What you see here on the right side, what is it now? For example, here, which was mainly related to strategy of China. So how much is consumed? I mean, Brian did a wonderful talk here, but just to get an idea, when we are talking about phosphate rock concentrate, and this was Brian was referring to, so with respect to 30% P2O5, we're talking about 220 million tons a year. And that brings us also to some issues and challenges related to how we perceive numbers. So what is it? What's 220 million tons? And this is the phosphorus actually that we consume a year. And when you imagine what that is, that's a cargo train that leads around the equator 1.3 times. I mean, this is something. So we are talking about volume, we are talking about impact, and this phosphate rock has to come from somewhere. So can we just substitute it by, say, for example, just so-called very green solutions? Let's be a little bit provocative. No, actually, you can't. I mean, we depend on the mineral resources, and I'm coming from Austria, and I could make a point, for these very green solutions. But yeah, maybe they work for some regions, as we also discussed today, but actually not for a bigger part of the world. So with respect to consumption, it's also not only, say, to consider population growth. We can say this is 28%, until 2060, but actually it's also about consumption patterns, meat consumption, prosperity increase. And this is also different with respect to the northern and southern part of the world. So that means also what Mahmoud was referring to, is there a special role, for example, for Africa? Yes, there is, because the demand in phosphor, there will be an increase of about 164% until 2060, compared to 24% in the Western world. And this is not only related to population growth or not growing population, but actually to consumption patterns in particular. So let's make a little jump to the other side. And I mean here with respect to supply side. And are we running out of phosphorus? What are the implications here? And what are the reserves that we can count on? And here is already one big issue. Reserves are not fixed. They are dynamic. And that means, for example, there is a dependence on prices. And that means if prices rise, so do stocks. And when we do calculations and simulations where we kind of consider stocks as fixed, it's just a problem in the calculation. And that also led to that kind of understanding that right now, so around 2025, 2030, there will be a phosphorus peak and that we will run out of phosphorus in 50 or 100 years. So that's not the case. And we can learn something from other raw materials, for example, from copper, and you see it here. So it was like in 1970, it was about 36 years. Then it was revised 43 years, and so on. And we see that actually that kind of calculations need to be revised and need to be rethought. And I think this is a very strong key message that we need to have in mind. So reserves, that's actually the phosphorus that can be mined, that can be consumed based on a market-related and technology-related feasibility. Resources, on the other hand, we know about them, but maybe the market is not ready for that. So meaning it's not economically feasible, or maybe there are still problems with respect to technologies. And so Brian mentioned the issue of technology. What is available? What can already be applied on the market? What is still at the stage of testing? So that makes a very big difference in here. I'm sorry, wrong direction. Yeah, so we heard about that. So is it now that we can count on the phosphorus resources for a longer time? Yes, and please let me make a very simple calculation. When we think about what's the estimation of phosphate rock reserves right now? USGS, I think it's 71 or 74 gigatons. So what is that? So that means that this is the kind of orientation that we have for the future. When we consider that we are kind of consuming 0.220 tons a year, meaning the 220 million tons of consumption, that leads us now to a calculation where we can say, okay, this is maybe 312. Some calculations suggested 330, but this is a big difference to the kind of fear that was going around in the last years or in the last decades. And make another thought experiment. When you think then not only about the reserves that we are aware about, and we know that that changes based on prices, new technologies, and all that, but when we think about a resource base and look at the USGS data, there we see that we are dealing here about 300 gigatons. And that brings us exactly to what you see up here. So do the calculation, and then we see we are beyond the 1,000 years. And this needs to be kept in mind. So it's the creativity, it's the technology, and it's the innovation capability that Mahmoud mentioned before that makes a difference. And I think this is also an issue why institutions such as GPI and the other institutions represented here are needed for that. And what I just said can be imagined here based on this box. So you see here on the upper left part, you see the reserve part. On the lower left side, you see the resource part. And on the right side, you see the geopotential. And be aware, this is not a fixed box. So the boundaries, they change. So that means that actually resources can become reserves. And that dynamics, this is the issue that makes calculations also difficult. But we know that actually what I presented before is just a kind of a minimum assumption that we have in here. So changes in prices make changes in technology, new technologies available, and also changes in the stocks. And that means also possibilities in improving inefficiencies. So I would maybe kind of extend what you said at the end, recycling, it depends. I mean, you can have efficiency improvements along the whole supply chain. So it doesn't start only at the consumer. Why should it? I mean, there's the place, there's the possibility, where we do the mining. So it's exploration, it's extraction, and thinking about possibilities, thinking about innovation makes sense. And this can be, I would say that can be more sustainable than just thinking about the end, so circular economy, maybe there's a little mistake in there when MacArthur Institution did the circular economy, great thought, but actually the loop not only is related to the end, but actually maybe along the whole chain. And this is something that we also want to bring up here. So that kind of feedback loop is represented here. So what you see here, that actually this changes based on imbalances on the market or based on developments, you see the changes on the supply side in the upper side, and you see also changes in the demand side on the bottom part here in that figure. What does that mean? I think also, as you brought it up, there's also a possibility, say, for example, not only for increasing efficiency and effectiveness, but efficacy, doing the right thing. This is also something. So say, for example, precision agriculture, and that means can definitely make a difference. And that's also the dynamics that we can count on the demand side. We know that there are different hotspots where we have high concentration of phosphorus. But there's also that kind of issue. There are only few examples, where we really can count on phosphorus. And this makes a difference also because of, say, risk assessment. And what we see here, this is like country concentration on the horizontal axis, and you see then also a country risk on the vertical axis. And I think that's good to have this kind of orientation in mind, because this is also the orientation that we are using, for example, for the critical raw material map in Europe or globally. So what we see here is actually also that for sure, there are huge deposits in Morocco, but there are also other deposits around the world and also other possibilities where, for example, young companies, young innovation drivers are also participating in this market. And I think this is important because, I mean, the most innovative and the most sustainable orientations might occur there, where not only one player is on the market, but actually where different sources and different streams are coming together. So you see the red spot in the middle. So phosphorus is in this map of the 33 commodities that are considered here in kind of the middle field. And this is good. So that means, is there no risk, no country risk? I mean, that would be a stupidity to say something like that, particularly when we see what's going on around the world. But it takes particular interest, and we have to be careful in order to do the things right and also do the right things. That was also kind of a core message that I wanted to leave here, because a lot of other estimations and calculations were done on what you saw before. And let me just skip over some other impressions and other work that we did here in very short. And please, as I said, you find supplementary material calculations also in this paper here. So what is phosphorus used for? I mean, for sure, in this community, it's for food. But this is not in every head out there. So it's 93% is used for food. Then there's the question, what about the batteries? What about biofuels? Biofuels just count for 2%. And when we talk about the batteries, and Brian Spears is not here, but he did a nice calculation and simulation where he showed that actually within the next 30 years, in his estimations, batteries might account only for 10% what phosphorus is needed actually in food for 1 year. So that makes a difference. And this is actually not that much. What I said before also with respect to when prices go up, also stocks go up, you see that also kind of exemplified here in calculations and regression modeling that we did for the Western phosphorus field here. So what's important in here is like that the cumulative tonnage, you see it on the horizontal axis, actually is an exponential relation with the grade. So why is there anyway this kind of, it looks like linear relation? This is because we have here a logarithmic scale. Yeah, another thing. I mentioned before demand side, supply side. And actually, when we are talking about the whole supply chain, the whole value chain, what is actually the use efficiency? And we are talking here about total use efficiency. And then we have also discussed in this group here, nutrient use efficiency. And when you consider the whole chain, this might be much lower. Why that? Because the system boundaries are differently. Because when we say, for example, total nutrient use efficiency, that means how much phosphorus at the input side you need for actually getting the phosphorus based on nutrition to the people. And when you say nutrient use efficiency, you just stay at the field, and that makes a difference. So therefore, also based on unit discussion that we heard, and when we say, why are the numbers so different? Because system boundaries are partly different. That's the thing. And that means also huge possibilities for the whole supply chain. This is very good. I see Abdallah looking at the watch, and I felt like 2 minutes are left, and you are right, 2 minutes are left here. In very short, when we have this process orientation, we also need this kind of, I think, system orientation. And then the middle part, you see, what I said also was part of total use efficiency is not only the mineral phosphorus, but it's also the natural phosphorus that's already there. So all that needs to be considered. And then what you see on the left side, the blue part, this kind of consumer and recycling related issues together with the right side, and that might be related to Spears and his colleagues, the water related impact, all that comes together. So what's the message in here? Maybe a supply chain orientation is needed, maybe a system layer orientation is needed, and also the agents were mentioned. So I think an integrated perspective where we have a supply chain orientation together with a system layer orientation and another layer where we say the different agents, the different preferences, the different orientations need to be considered there. So that's actually a key issue. And when I said Mamu mentioned the differences between Africa, between different parts of the world, this is expressed here. So we did calculation here. You see the details when you go into that. So where we expect growth, population growth, where kind of we have behavioral patterns that change over time. So it's also a cultural issue where we eat meat and not only the GDP related issue that increases the meat consumption. And again here, this is just like thinking about where do we have potential to improve the process. And this, I want to make a strong point here. When we are talking about losses, that sounds sometimes so negative. Losses are maybe just overseen opportunities for the future. So it's like, what can we do along the whole supply chain to improve the system? And say, for example, I mean, let's think about Morocco. The slurry pipeline, was something that actually improved the efficiency. So it was not only a technological innovation, but it was something that helped actually to improve efficiency, improve health of population, in the surrounding of the production facilities. So this is something, and we see on the right side the possibilities along the whole system, from residues in mining, tailings, and so on. So along the whole system that should be considered. What does that mean? All that is a kind of possibility for innovation. And one could say it's like that kind of challenges are maybe the raw diamonds of innovation. And I was Schumpeter professor in Boston. And actually, what is innovation all about? Sometimes things need to hurt. And when things hurt a little bit, you get the attention of population also. And so therefore also sometimes it's a smooth way, sometimes it's a demanding way, sometimes it hurts. And all of it goes together in an innovation potential. This is a kind of a message here. And what we also heard, new technologies, Brian was mentioning, new forms of phosphates, also new processes. And therefore, let's think in portfolios where we say, what's the feasibility? What's on the table at the university, but what's kind of feasible for industry within the next 10 years based on investments, but also based on availability of technology. And that things should be taken into account. And from a sustainability perspective, it's not only the pollution side, but it's also, say, think about how to get access to low grades. This is something. And at the beginning, I showed you the copper example. We are talking now about 0.5% copper grades, that make already sense in doing the investments. Wow, what a big change over the years. And this also is something when we think about phosphorus, what are the possibilities in here? So it's like the cost, it's like the market situation, the investment situation that actually can make a difference. So therefore, what might be something that is unused right now might be useful in the future. And so therefore, I think this kind of axis between technology, between systems constellations and coupled systems is very important to have in mind here. That was it in very short, and this is like a slide finishing what I tried to present here. So because, I mean, what is it all about? Is it just about improvements in efficiencies? No, I don't think so. What you see here to the left side in this picture is like a current vulnerable state. Might be related to environmental factors, might be related to internal factors. And the question is how to get more resilience into the system, or some of you might say how to get the system to become more sustainable. And I think, I mean, this requires actually not only the science and the disciplines to be stronger and to work together, because this also not only occurs, but gets together with the agents along the whole supply chain. And this is what I would consider as a transdisciplinary approach, integrating knowledge of a smart farmer, and this is also a knowledge agent in the system, and bringing that together with the rest of the system, or bringing together the knowledge of a smart worker at the mine site with the system understanding of extraction. So this is what I wanted to point out here, and as a kind also of a vision, not only shared in our lab, but where I'm also happy that we had the opportunity to do some work here, what I demonstrated here in this collaboration with GPI. Thank you so much. So I hope I was able to take away a little bit the fear of rock scarcity and,
Yeah,
and
1300 years, very happy. Any questions or comments?
Please.
Andrew?
Sure. Why do you think that that narrative of peak phosphorus continues and persists?
Because it's, I mean, sorry for being a little bit sarcastic, because it's convenient sometimes, because sometimes people do not make the effort to rethink what's going on. So don't get me wrong, Dana Cordell did not do just like a wrong modeling. Actually, she did, I think, something beautiful. I mean, she made us aware about phosphorus is a critical issue to think about. So that's the thing. And when she said, I mean, there's the peak and that stuff, yeah, I mean, she did her PhD. Seriously, I mean, that was PhD work, and there were mistakes in there. And the modeling that we do in economics and all the other fields, are that model's always right? So I think great starting point, but also a necessity to rethink what's out there. And as I said, there are also some issues in there that make it difficult. I mean, when, say, for example, when you have articles in Guardian, Nature Sustainability, and you are, for example, a young researcher or not so experienced in the field, you go into it and you say, oh, nature, beautiful, so I take it. I mean, we should not blame just like the people working here, but we should motivate actually to make the extra effort to better understand what's in here. And another thing, just, I mean, sorry, to add that, I think it's also what I presented in here is very much based on knowledge integration across boundaries. Meaning, for example, having someone from geology talking to a social scientist, you know, to a nutrient scientist, is that easygoing? No, it's not. And actually, also as a matter of fact, pragmatic issue, you get most probably more impact factors if you stay in your own field. If you do the extra work, maybe you do not get like the benefit in the first moment. So I think it takes something, and it takes curiosity, and I would say maybe a core issue of science, which is science for the public good, should actually be in the center of the universe for a scientist.
Thank you. Thank you both for a very insightful presentation. And leaves us optimistic and interdisciplinary approach. And for collaboration, this is the right forum. You know, the people are here, so I would encourage people to talk to Global Phosphorus Institute for possible collaborations. Okay, next. Our next speaker is Dan Obenar. Um, uh, his research focuses on the integration of modeling techniques to improve our understanding of complex environmental systems. His research team has developed nutrient transport models across the United States, as well as predictive models for algal blooms and hypoxia in lakes and coastal areas. And I think your talk is going to be on STEP Center work.
Mhm.
Please go ahead.
Yeah, thank you so much.
Yeah.
Okay. Thank you. All right, hi everyone. Thanks for sticking around for the presentation today. I'm going to be talking about a new initiative. It was created by, should I be talking into this per Zoom? Okay. I feel like, I think, is it just for the people in the room or? Okay. Can you all hear me in the back? All right, okay. Sorry, I'm used to teaching a class.
Use the microphone, please.
I'm using the microphone.
That's
which
hard.
is that working?
Is it on?
How about this one?
Oh, hello, there you go.
Yeah, there you go.
There you go.
There you go.
Thank you. So yeah, I'm gonna be talking about a new STEPS and SPA initiative. It's identification of priority lakes and watersheds for nutrient intervention. This is a project being funded by STEPS. Sometimes we just refer to it as the Priority Lakes Project for short. We're just getting started right now. It just got funded. One of the things that makes this work unique is we've been working with institutional collaborators. We've been meeting with them to develop the proposal, think about what our priorities need to be. And you can see some of them listed here. So this is the Association of Clean Water Administrators, North American Lake Management Society, U.S. Army Corps of Engineers, USDA, Department of Agriculture, EPA, Fish and Wildlife Service, USGS, SPA, of course, and University of Illinois. And if you're interested in getting involved, reach out to me or one of the co-PIs. You can see there, some of the STEPS members who have been involved in the work so far. All right, so a little bit of motivation. Probably y'all are fairly familiar with this, but there's a large amount of phosphorus flowing through the United States. About 4 teragrams per year enters agricultural and urban systems. And about 4% of that agricultural input is lost to waterways, and about 13% of urban and household inputs are lost. So that would be like urban fertilizer, wastewater treatment plant outflows. And so obviously, as we all know, that creates some problems downstream. So these losses, or as Gerald referred to them as opportunities, if we don't deal with them, they are major drivers of nuisance and harmful algal blooms and other related issues like hypoxia, which is sometimes referred to as dead zones. According to the US EPA, about 50% of US lakes are in poor condition for phosphorus. Similar percentage for nitrogen. Obviously, there's a lot of overlap in those lakes. But really, given how widespread this problem is, and given limited management resources, how do we make decisions about where to provide nutrient interventions that will provide the greatest water quality benefits, ecological benefits, and societal benefits? Okay, and just to provide a little bit more background to kind of put what I'm going to talk about in context, I'm going to probably use the word eutrophication, which probably many of you are aware of, but maybe not everyone. And it's generally the increase in organic matter, often measured in terms of algae in water bodies, right? And typically, in most water bodies, it's nitrogen or phosphorus that's going to be the controlling factor. And to some extent, algae are good, right? Because it results in a productive fishery. But in some cases, we end up with excessive algal biomass, and that can lead to a lot of issues. So for example, it can result in oxygen depletion, which can result in fish kills or metals releases from bottom sediments. Of course, it can result in aesthetic problems too if you have unsightly algal scums and other issues, fish kills, of course. It can produce taste and odor compounds and algal toxins like cyanobacteria toxins, which have been in the news a lot over the last decade. And so, ultimately, this can lead to a reduction in industry, coastal industries, industries near lakes and waters, reduced recreation, and of course, related to that, increased treatment costs for water supplies. And this is really just focusing on human and engineering issues, right? Of course, there's a lot of ecological issues as well associated with eutrophication, other additional concerns. So what do we do about this? Well, there's a lot of management being done at the local level, but a lot of resources are allocated nationally. And there's a lot of great new data sets that are emerging that allow us to think about eutrophication issues and nutrient management at a national scale. And so just as an example of, one of these national scale studies, there's a number of them coming out. This is work that my student did who combined a lot of water quality and related data and was able to make predictions of bottom water temperature and surface water total phosphorus concentrations in large lakes across the entire US. And those might have some value in their own right, but why do we want these? So what we were able to do is we combined these with a statistical model to estimate the internal loading rate of phosphorus in lakes and reservoirs. So how much legacy phosphorus is coming out of those the bottom sediments in those lakes and reservoirs. So we put all this together, these machine learning and statistical models, and could make estimates of that throughout the US. And then we can compare that to things like point source loading, so wastewater treatment plant discharges. And in certain areas, in the summer at least, you have comparable amounts of phosphorus loading from both wastewater treatment plants and internal loads. And that has a lot of management implications that we don't have time to get into, but it's just an example of the kind of project that we can do now thanks to all of these data sets. Another example, this is done by folks at EPA, and now we just did 6,000 lakes. They're doing 100,000 lakes, so even very small lakes across the country. And they're looking at predicting algal levels, and you can see what are the estimated algal levels across all these lakes, including lots of lakes where we don't even have any monitoring data. And the ones that are red are, as you might expect, are the ones that have the more problematic algal concentrations. So that's another example. And then the work that we've been doing working on with Jim Elser and my lab group is looking at, all right, so which of the lakes are going to be most responsive to phosphorus versus nitrogen? So here we're looking at, the lakes that are shown in red. These are fairly large lakes. And the lakes that are shown in red are the ones that are more likely to be responsive to phosphorus. The lakes in blue are more likely to be responsive to nitrogen, and in between are co-limited lakes, okay? So again, just some examples of what we can do and what is going to hopefully feed into this project. And so as I mentioned, we've been having these meetings. Matt Schultz has really been helping, with the SPA, has been helping coordinate everything, meeting with these institutional collaborators. And I've taken a little liberty and tried to distill down some of, what we got out of those meetings into these 5 main points. All right, so throughout this project, one of our goals is to, again, synthesize the latest data sets for lake and water quality conditions, as well as watershed inputs and socioeconomic conditions. We do want to consider both natural and man-made lakes, in other words, reservoirs. And as I alluded to in the previous slide, we want to be thinking about nitrogen and phosphorus because we need to think about both when we think about these eutrophication endpoints, like harmful algal blooms and hypoxia. Now, we may focus a little bit more on phosphorus in terms of solutions because we're a phosphorus center, but we need to consider both nutrients. And then we want to consider not just the water quality, but also where is there the most opportunity for improvement. And so again, instead of thinking about this phosphorus export as losses, we can think about it as an opportunity, especially if it's from a controllable source versus maybe more natural erosion and things like that. And then also, where are there vulnerable populations or vulnerable industries that would be more susceptible to these eutrophication issues? And finally, we want to develop a robust workflow so that as new data come out, we can update the system in the future. So I'll go through this pretty quick, but I just want to point out that again, we've already identified a lot of great data sets, and again, a lot of this is hot off the press. There's been a lot of progress in the last 5-10 years in terms of developing data that we can use to make these national assessments. This is a compilation of of all the chlorophyll data, or at least most of it, collected in lakes and reservoirs across the United States. It just came out in 2024. There's also a remote sensing based estimate of this that was developed by USGS recently. And of course, we also have a lot of new data related to other things that we care about, nutrients, dissolved oxygen concentrations, and even algal toxin data. Those are the hardest to get, but even that's becoming more available now. For watersheds, one of the great resources we have is the National Nutrient Inventory that's developed by EPA. So it includes like the fertilizer manure inputs, but also like domestic urban inputs as well. We have better information about wastewater treatment plant flows and phosphorus loads. And of course, more conventional data like land cover and census data for socioeconomic conditions. All right, and so here's kind of the scope of work we developed. So as alluded to on the previous slide, a big part of this is task number 1. So we're going to be developing a comprehensive database on lake and watershed characteristics for the United States. Number 2 is, even though a lot of these data sets are really nice, they still have different levels of coverage. Like some may be only for large lakes, or just certain lakes that were monitored. So how do we impute missing data? We need to prioritize our time to think about, how we're going to deal with some of the data gaps that still exist. We need to assess the potential efficacy of nutrient management across lakes. So again, where will nitrogen or phosphorus lead to the largest reductions in algal levels and other eutrophication issues? And then again, as I mentioned, the socioeconomic and ecological benefits. Where would we expect to see the largest benefits? And we want to put this all into a systematic framework. And that's where, our grad student and postdoc, well, they're going to be working on all of this, but this is where we're going to need to, be creative about how we do this and work with our institutional collaborators so that we can apply this framework based on people's priorities to look at, again, how we would prioritize lakes and watersheds for nutrient management. And we also, of course, want to be working with knowledge transfer folks on online and other resources to make this widely available. This is hopefully going to be a 2-year project. In year 1, which is just getting started, we're going to be focusing mostly on items 1 through 3, but we do hope to start playing with the prioritization framework. And then in year 2, we're going to be focusing more on items 4 through 6. So again, we're getting started. There's time to get involved if you're interested. And again, we're going to be working with those institutional collaborators from those various agencies and organizations to provide feedback throughout this process. Not a lot of Zoom meetings, some Zoom meetings, and hopefully meeting in person once or twice. Here's the references. Don't have time to go through them, but if you're interested in some of these data sets, and again, that data set list is by no means comprehensive, but these are some of the ones that we've been thinking about recently. I think they're going to make these slides available later. And again, here's our project team. So you can see, a number of folks, some of whom have been involved and others who we hope to get involved later. And so that's what we're up to. If you have questions, I'd be happy to take them now, but also there's my email address, or feel free to reach out to any of the other co-PIs who you may see around over the next couple days. So thank you.
There's a question, yeah.
Jacob, yeah.
For the prioritization piece, have you given thought to frameworks that you might use? I mean, it's more than prioritization, it's decision making, right? So I think about multi-criteria decision analysis, and I just wonder, have you scoped this out?
So we thought about including some kind of numerical multi-objective optimization in the first couple of years, but we felt that that would be a bridge too far. We want to start thinking about how these outcomes are correlated with each other, right? And we want to start thinking about, what do the stakeholders, these different organizations think of them. So it may be a little bit more subjective in terms of how you weight these different factors in the first 2 years, but we definitely see this potentially feeding into a more quantitative optimization exercise in the future.
Yeah, and I'll just jump in. This was all inspired by the American Rivers Association, which names America's most threatened rivers every year, a list of 5 of them. usually they're threatened by like water withdrawal or something like, so we first imagine this would be America's most threatened lake. And that would be a way of getting a lot of attention, but I think that it might be more nuanced than that when we finish.
We do hope to get some attention, yeah.
Just let me know.
Yeah.
Ben, wonderful presentation, thank you. May I ask you, is biodiversity maybe also a dimension that could be considered in your model?
Yeah, I think so. The question is about biodiversity in the model. I think absolutely that's one that we haven't given a lot of thought to, but we do have a representative from the Fish and Wildlife Service. So we're going to be reaching out to them, thinking about like where, according to the Fish and Wildlife Service, we have biodiversity or endangered species and things like that. And again, I think, we might at some point give some list of like these are the most, endangered lakes, but I think that really what we're trying to do is provide a framework. And like if Fish and Wildlife Service thinks that, from their perspective, that biodiversity is the main issue, they can weight that higher in their analysis. But yeah, I think that will hopefully be something that we can incorporate. Thanks.
Any more questions? Thank you, Dan. For writing. Yeah, very clear and focused presentation, concise. Okay, the next speaker is Dr. Anna Maria Martin. She's a JD from the University of Virginia School of Law and a PhD in political science from Northwestern University. She's currently an associate professor of sociology and law at the University of Illinois. Her research focuses on governance and policy, making on environmental issues associated with agriculture. Go ahead, please.
Thank you. It's on, yes. I'm delighted to be here to talk to you also as a member of STEPS about some of the initiatives that we are going to be pursuing in our research agenda on policy and governance. I'm going to start by talking about some of the challenges in policy and governance for phosphorus management. Then I'll talk about some specific research projects that we've got that we're getting started in STEPS. And then I'll conclude by talking a little bit about the policy forum, where your input would be much appreciated. So an undergraduate working in the STEP summer program once asked us, who's in charge of policy over phosphorus in the government? Is it like the Department of Phosphorus? And all of us working in governance and policy thought, oh, if only, that would be a dream come true. But we all know, and I don't have to explain this to anybody in the room, that the regulatory environment governing phosphorus is way more complex, right? It is not restricted to any one sector. It involves agriculture, the environment. We heard this morning, it involves finance and insurance, banking. So it sprawls pretty much across a lot of governmental sectors. We don't have any control over the scale of governance, right? Local regulators, state regulators, federal regulators are all interested in phosphorus management, and our friends in Europe can tell us all about international regulators and the EU. There are a variety of different kinds of instruments, policy instruments that cover phosphorus management. So taxes and incentive programs are familiar to all of us. My colleagues in STEPS don't think it's funny when I say I love a good lawsuit, but I do. I love a good lawsuit. Litigation matters. But again, we heard this morning that insurance and the creation of market mechanisms, those also matter. And then we in STEPS think very widely about what counts as policy and governance. So it's not just government regulation and laws and statutes, but it also includes standard setting bodies, for example, contractual agreements. And now, after this morning, I have to start thinking about insurance contracts, right? So this is massive. It's huge. It is almost impossible to get your hands around. And we found in phase 1 of STEPS, where our social science program was mostly focused on adoption, we kept running into stakeholders who had all kinds of issues with regulatory obstacles. Wastewater treatment, for example, operators are constantly worrying about permitting standards. And sometimes those permitting standards are important. You got to hit your targets. And that can discourage innovation, right? They're worried about taking risks in case they don't meet their targets. We also found in agriculture, watersheds don't really care what county they're in, nor do they care what state they're in, right? And so watershed planning commissions seem like a great idea for controlling best management practices and water quality, but water planning commissions can't control policy necessarily. And then another governance mechanisms that's incredibly important are best management practices, right? But who gets to say what they are? In Illinois, we have a pretty transparent process. I know who gets to say what best management practices are, and one of them is in the room. But other states, it's not quite so clear, right? So these are some of the things we kept finding. After phase 1, we basically concluded that law, and this is something any lawyer will tell you, law doesn't always successfully keep up with innovation. Law isn't always that flexible. Laws and regulations are sometimes based on things other than evidence and other than scientific expertise. And then in addition, we also, those of us working on these projects in STEPS, also think about institutions, that we need to sort of think beyond just government when we think about the kinds of institutions that can govern phosphorus management. And we have really good experience with that in Illinois as well. So some of the research that we'll be doing in STEPS in phase 2, one initiative we have is an initiative on policy design. This is going to be led by Jonathan Koppas and Justin Baker, and draw on resources at the University of Illinois' Policy Design Lab. Jonathan has sort of hair-raising stories about the way conservation policy can sometimes get written. Sometimes policymakers don't always know things about the impact that their policies are having. So this policy design initiative is hoping to bring together some of the work. Dan, I know you're going to get a call. Some of the work that Dan described, bringing together public data sets, computational modeling in both economics and environmental modeling, and make it usable for policymakers so that they know they can connect the conservation programs they're designing to actual impact on, for example, water quality. In addition, we are all big fans of Elinor Ostrom, Nobel Prize winning. She won a Nobel Prize in economics, even though, yay, she was a political scientist. And Elinor Ostrom developed a lot of work on collective governance, where the basic idea is the people who are in a best position to craft solutions to problems are the people who deal with those problems every day. And for us, in STEPS, we think of the soil and water conservation districts, which are across the United States, as being a really interesting example of that kind of collective governance. SWCDs are often the gatekeepers that provide scientific knowledge to ordinary producers. So they offer technical assistance on things like cover crops and nutrient management. But more importantly, they are embedded in communities, in the social networks. And one of the things we know about farmers, when they're thinking about how to adopt practices, they often turn to their neighbors. So soil and water conservation districts seem like a really promising governmental entity that can help foster adoption, but we also know that across the United States, they vary in terms of their resources and activity. And so we have this research project that's going to do a little bit closer research on how and why soil and water conservation districts can succeed. And then we are sponsoring a policy forum. And we have a couple of different projects in mind associated with that policy forum. The first is to try to wrap our hands around that regulatory environment for successful pea management across sectors, across sources, across instruments. And I could hire a very smart law student to help me with that, but I don't think that's the best way to go. I think that we are going to try to, we'll do that, but we'll also try to document this regulatory sprawl by consulting with our stakeholders. Just talking to people like many of you in this room about what your main regulatory hurdle is. What are some of the opportunities that you have in terms of policy? And we're going to try to develop that picture from a wide variety of different stakeholders, industry, advocacy groups, and regulators as well. And then our plan for the policy forum is to also conduct workshops with stakeholders where we actually try to tackle some of these regulatory hurdles. So we can find perhaps pathways through policy, ways of improving policy, making policy more responsive, more nimble. But we're also going to be looking at different institutional obstacles, institutional drivers of innovation, and possibly alternatives. And our goal for the policy forum is that we do actionable research that can actually help promote greater, more effective phosphorus management and hopefully make some policy recommendations. So those are our plans in the next phase of steps, and I'm happy to answer any questions. Yes.
For your policy forum, are you focusing on a specific region or state like Illinois, or are you looking nationwide, or what's your plan for that?
We're hoping to make this nationwide, and in our hopes and dreams, we also like to make it international, global. But yeah, we're not committed to any one particular state, although we're still very much in the planning stages, so we may do them regionally and then have one big payoff. But no, STEPS as a center is not focused on any one particular region. Yeah.
So our next speaker is Steph Kulesek. Yeah. And she's an associate professor of nutrient management and animal waste at NC State. She's the incoming chair to the Sarah 17 group, which focuses on reducing phosphorus losses from agriculture. And I think you present an update on Sarah 17.
Yes, I will try to be as brief as possible. Give me a sign at 10 minutes and I should be done by then. So, hi everyone, welcome to NC State. I don't know if anybody from NC State officially welcomed you, but welcome to my hometown. I am the incoming chair for the Sierra 17 group. That name doesn't mean really anything, Sierra 17, except for that is the name or the code for the group. So it's Southern Extension Regional something. And it's number 17. So it's a weird name, but the whole goal is to understand and minimize agricultural phosphorus losses. And so wanted to talk to you a little bit about what this group is about and hopefully get all of you to join and sign up. So while you're out there, Google Sierra 17 and on there it'll tell you how to get on our listserv for emails. So again, the mission is to really advance the science. So this is a group of scientists, whether that is government, whether that is extension educators, whether that is university researchers. We have a lot of different expertise in the room and a lot of different work groups based around people's interests. So regionally, there's a lot of different things. For instance, drainage. That's not something we use it a little bit here, but not a whole lot up in the Midwest. There's a work group focusing on that. So there's a lot of different things that you could be a part of if you're interested in advancing the science. That's our number one thing. And Sierra 17 has a long history of helping advance the science. So it started in 1996, which is crazy, about proper phosphorus management. And then out of that came the National Phosphorus Project. And you can see here how many locations were involved in that. So even though the title says Southern, that doesn't mean that you can't be involved. It just means that that's where the website is hosted, is here. That's basically it. And so you can see that we've hosted events all across the country. 2 years we hosted for a half day after ASA or the Tri-Societies meeting. So it's very easy to attend if you're already attending that meeting. And every third year we go to a site where someone wants to host and show us what innovative things they're doing in phosphorus management and what science and capabilities they have in that area. And those are always a great time, and we always get to dive into local issues, which is always very interesting. There's been a lot of publications that have come out of this group, a lot of position papers, white papers on the thoughts and consensus of the scientists in this group to kind of move, again, science forward. And so phosphorus indexing, I don't know if you saw the picture a few slides ago, but phosphorus indexing was introduced through this group. And it's crazy that it's widely used now. Like it really is something where the leaders in phosphorus management are coming together and trying to figure out consensus around the science topics. There's also a lot of we heard BMPs are important. There's a lot of fact sheets that have come out of this group around BMPs, and then also their standard method manuals. As far as work groups, we had a legacy phosphorus work group, and Andrew led a paper talking about people's perspectives. We also surveyed the group of Sierra 17 and asked them, what is legacy phosphorus? Because that is always a question anytime you talk about legacy phosphorus is, what is it? And people have some different opinions. And so we polled the group and got a lot of different opinions, and that was synthesized to kind of lead the discussion forward. Again, with this complicated topic, we're trying to build consensus. How do we do that with so many varying opinions? And there was another publication that came out as well. Phosphorus and drainage waters, this is another work group. And they have a lot of different activities, whether that is actual field level research projects that you could be collaborators of, or looking at the modeling aspect. There's a lot of different opportunities to get plugged in there. There's also a newer work group which is focused on phosphorus in stream banks, and so how stream bank erosion contributes to phosphorus losses. And so that is a newer group, but is really interesting. I think there's a lot of excitement or enthusiasm because it's a newer group. They are also updating the phosphorus methods manual, so that is in process right now. And so if John Kovar is the one who's leading that, so if you feel you want to be plugged into that, there's that opportunity. And then there's this, I don't know if you'd want me to call it critical source area or not. I mean, some people have feelings about that, but there's this GIS kind of looking at those areas and how we can really create practices to target areas of higher risk of loss. And so that is called the Precision Conservation Work Group. And that group is, I think, a lot focused on the modeling part of things and also how can we use the GIS systems and tools that we have right now to then target those areas in the field. We just started this year giving out an award because Andrew Sharpley was a big part of CIRA 17. And so we created an early career award in his honor. And the first person who got it was Andrew. I think he actually stepped out of the room. So make sure you pat Andrew on the back for his award that he received this year. And so if you're plugged into this group or if you know any newer scientists who are really pushing that phosphorus science forward, then we would love to have them submitted as a candidate for this award. And our future meeting is going to be again right after the Tri-Societies meeting, which will be in Portland, Oregon, November 1 through 4. And so it's a half day after that. So normally people are flying out Wednesday night and Thursday morning. We tend to fly out on Thursday afternoon, and that way we can just stick around for an extra half day and do work group stuff and also get updates and whatever else is on the agenda. So happy to chat more, but I don't think we have time for questions. Hopefully I kept us a little bit on time.
Thank you, sir, for excellent presentation. And this is a very peace-centric group. Great contribution they are making, so really appreciate. So our final speaker is Jeff Constantino. Jeff serves as Communication Director at ReFed, helping the organization to connect to its key audiences with engaging and actionable content. Previously, he oversaw communications and marketing at the Western Union Foundation, which works to empower refugees and other migrants with education and workforce training. Yes. It's this one. Hello.
All right. Thank you so much. I'm really excited to be here. I realize that I'm the last speaker before the reception, so I will move quickly. I'm here to talk about food waste. And as you heard, I'm not a scientist, I'm not a researcher, but I'm here to give you just a broader overview of food waste to help set the stage for future discussions. So obviously food waste is something that we're all familiar with. I think we've all scraped some leftovers into the garbage bin, like you see in the photo here, but hopefully as you'll see, it's a much bigger problem than what we're doing in our own kitchens. It's something that affects the entire food system, which makes it difficult to address, but that also means that there's a lot of opportunity connected to it. So as you heard, my name is Jeff, and I work for an organization that's called ReFed, and the name comes from the phrase rethinking food waste through economics and data. We're a US-based nonprofit. We work with food businesses, we work with researchers, funders, policymakers, and more, all to help solve food waste. And we are known for our data. That's the thing that I want to point out on this slide here. As you can imagine, data is very difficult to come by. Most people, of course, don't measure how much food they waste in their own kitchens. And believe it or not, up until very recently, most businesses didn't measure how much food that they were wasting. So we have been working hard to gather data from a number of different sources to help paint the picture of the extent of food waste and its impacts, and to characterize dozens of different solutions. Despite the extent of the food waste challenge, though, we're very optimistic that it's a solvable problem. It will take money, of course. We estimate that about $16 billion per year invested into solutions for food waste across the entire food system could reduce it by 25%. And this is just based on the solutions that we have modeled. We've gotten through about 40 of 80 plus solutions that have been identified. And so obviously this information can change, but that investment though could yield a 4-to-1 return. And then you can see a number of other impacts on the side there. Job creation, meal equivalents, water savings, greenhouse gas emissions. It's really one of those triple bottom line things. It can affect the economy, the environment, and has social impacts as well. And in fact, the climate nonprofit Project Drawdown has listed food waste reduction as one of its top solutions for climate change. As we talk about different opportunities that come from reducing food waste, there are also opportunities for phosphorus. As you all know, of course, when food is wasted, phosphorus is wasted. I'll tell you honestly, REFED has not done a lot of research in this area. We don't have a lot of information on this yet, but our data team estimates that there were approximately 195 million kilograms of phosphorus in surplus food in 2022, the most recent year we have data for. I'm just going to read this because I obviously don't understand all the details. That was determined by taking all of the foods that we are tracking for our other estimates, including categories like breads and bakery, dairy and eggs, dry goods, produce, etc., determining their dry matter content, and then applying a standard estimate of 0.01 kilograms of phosphorus for each kilogram of dry matter. So that resulting amount is about 11.5% of the 1.7 kilograms of phosphorus that were used in agriculture for that year. So I don't know if people out there have more details on this. They're looking at this slide thinking, oh my God, that's so wrong, but that's what we have come up with. And so clearly this is just a rough calculation. It depends on the type of food that's being wasted and other factors, but it's yet another reason for us to strive to make our food system more circular rather than it just being linear from farm to fork and then actually disposal. I'm not going to go too deep into this, but just to say that there's just various terminology around the issue. We talk about surplus food a lot. Food waste is the largest portion of that. You may also hear people talking about food loss, which is actually food waste. It just depends on where it's happening in the supply chain. There's actually a big push just among organizations like REFED, to use just the term food waste to make it easier for people. When I first started working at food waste, I noticed that a lot of my friends no longer wanted to go out to dinner with me because invariably we'd get to the end of the meal and, obviously they'd still have food on their plate and they'd be pushing it around with their fork, trying to make it look like they had eaten more. And my reaction was always, look, this is just a much bigger problem. It's not something that we can eat our way out of. And you can see that 31% of all food goes to waste, and the way we try and just bring that down, obviously, to the individual level, to get people engaged in the issue is to say it's like getting 3 bags of groceries, dropping one in the parking lot on the way to your car, and then just driving off without it. This is how much, from a consumer perspective, we're spending on food that's never eaten, so imagine that for a family of 4. Consumers are the biggest source of food waste, but as you can see, it is something that happens across the supply chain, which means that it's not one single problem, but a whole bunch of other problems that all add up. And if you think about the picture of the scraping the broccoli and beef into the bin on my title slide there, compare that to thousands of pounds of broccoli that are going unharvested on a farm because labor costs are too high compared to what you could get for it at market. So it's a really complex issue, but that also means that there are a number of ways to get into it. And so there's not just one silver bullet solution. I'll just go here real quickly. Just in terms of environmental impacts, you can just see 16% of cropland use is due to food waste. It's the area size of California and New York combined. 16% of US fresh water use, that's like all of us in the US taking 7 showers per day. 4% of US GHG emissions, which is like driving 54 million cars over the full year. And then it's 24% of landfill inputs, which is the number one input to landfill. And it also is the number one source of methane from landfill, which is something that the EPA just came out with. 60% approximately of methane from landfills is from food. Obviously, it's also a global issue around the world. About a third of all food produced goes to waste. That's about 1 billion meals per day. $1 trillion in value and 8% of global GHG emissions. And if food waste were a country, it would be the third largest GHG emitter behind China and the US. And the other issue, obviously, is that we are facing a growing population. We have more people to feed. The UN estimates we'll need 50% more food by 2050. But that is coupled with the fact that climate change is causing decreases in agricultural productivity. So we really need to make better use of what we're already producing. And as I think most of you probably know, food waste is related to the UN Sustainable Development Goals. Nobody wants to wake up and waste food. It's lucky that it's one of those issues that people just feel, inside that it's the wrong thing to do. It's actually one of the few nonpartisan issues out there now, which we are lucky as an organization to be aligned with it. So obviously then the question is, why is so much food waste happening? I'm not going to go through every single thing here, but I do want to just point out again, it's a lack of data. It's hard for businesses to forecast and understand how much they should be ordering if you're a restaurant or if you're a retailer and such. I also just wanted to point out culturally, we still haven't gotten to the point where wasting food is something that has risen to the level of some other issues that society would admonish you over. So we always say that if somebody was walking down the street and threw half a sandwich on the ground, somebody would probably say, hey, don't litter, instead of, hey, don't waste food. As I said, though, there are solutions. There's lots of them. We as REFIT are in the process of modeling them to show what their impacts would be in terms of how much food is diverted from waste, net financial benefit, etc. This just categorizes the different solutions, the colors, the ones at the top in that sort of, what is that, yellowish green? Can't tell from here. Those are the ones that we have actually modeled. There's also best practices on here as well. We categorize them according to these 7 key action areas to help focus the thinking of the food system. And these are just some of the many organizations that are involved in implementing food waste solutions. So there's a lot of activity in this space, and we're excited to be at the center of it. I wanted to highlight a research tool that we have that you may find beneficial. It's called the REFIT Insights Engine. And all of the information I've talked about, as well as a whole lot more, is featured here. It's an online knowledge hub. It's free, it's available for anyone to use, and it has these 6 tools. This is a view of the food waste monitor, which digs into the extent of food waste along with its causes and impacts. And you can use the drop-down menus at the top to explore different outputs, sectors, years. This is a view of our solutions database, and it goes much further down the screen. But this looks at the range of different solutions that are out there and looks at different impact metrics. This is something we call the impact calculator, where you can actually type in different scenarios. This is what I'm doing now. What if I did this? And it will let you compare them and see what implementing specific solutions could achieve. We are also creating a food waste chatbot. It's actually in use internally at the organization, but we're going to be announcing it being public early next year. So that's something that would give you access to all of this refit data, but any other food waste data that is out there as well. We have various publications. This is our annual food waste report. The next one is going to be coming out in April 2026, but it talks about trends, data points, etc. And then if you are really, really interested in food waste, we have our own Food Waste Solutions Summit. It's going to be in May of next year in Charlotte, North Carolina. So I'm looking forward to that because it's just a 2.5-hour drive for me. This year's was in Seattle, which took a little bit longer to get to. So that is everything I have. Thanks so much for listening to me. We always say that when people start thinking about food waste, they start seeing it everywhere. So I predict that you're going to be at the reception and out to dinner tonight and really be scoping things out. So thank you.
Thank you, Jeff. So with this closing talk, I would like to thank all of our speakers for such impactful and wide-ranging work they shared with us. And it seems like we are making a lot of advances on phosphorus sustainability front, but there are also concerns like food waste, eutrophication, and I think we need to accelerate innovation on those fronts as well. So let's give a big applause to all our speakers and enjoy the rest of the forum and the reception. Thank you.
Great. I also want to thank everyone who spoke and took the time to share their ideas and information with us. It's a really fantastic session. I want to especially thank OCP for sponsoring this session. The leadership and collaboration that the Alliance has had with OCP over the years is greatly, greatly appreciated. And thank you, Amarjeet, for doing an excellent job as chair. And let's go have some refreshments. All right, let's go.